So the problem says that the hypothetical semiconductor has an intrinsic concentration of this much, so 1.0 into 10 to the power 10 per centimeter cube, and the temperature is 300 K, and conduction and valence band effective density of states is NC and NV, both are equals to 10 to the power 19. So NC and NV I will write in the next page. NC is equal to NV equals to 10 to the power 19 per centimeter cube. So we need to find the band gap. So if we recall the formula, Ni square is equal to Nc times Nv e to the power minus Eg over Kt. If we use this formula, it becomes e to the power minus Eg over Kt equals to Ni square over Nc times Nv, and we need to find the only unknown here is the band gap, which we need to find. So this one is 10 to the power 10 square, and this is 10 to the power 19 square. So that becomes e to the power minus Eg over Kt equals to 1 into 10 to the power minus 18. If we do that calculation, and then if we take ln on the other side, it becomes Eg over Kt, and ln of that gives me minus 4.14 into 10 into 10, basically minus 41.4465, like that, something like that. And then this is Kt, so Eg, this minus sign goes away, Eg is equals to 41.44 times 300 times 8.6173 into 10 to the power minus 5, which is the Boltzmann constant. That gives me 1.06, which is the band gap, 0.06 electron volt. Number B asks, if the semiconductor is doped with Nd is equal to 10 to the power 16 donors per centimeter cube, what are the equilibrium electron and hole concentration at 300 K? So Nd is 10 to the power 16, which results in, so B, since Nd, so N will be equals to Nd, which is 10 to the power 16 per centimeter cube. So that's electron concentration, and law of mass action gives us this formula. So we get hole concentration as intrinsic carrier concentration squared over N. So that's 10 to the power 10 squared divided by 10 to the power 16, which is 10 to the power 20 divided by 10 to the power 16, sorry. So that's 10 to the power 20 divided by 10 to the power 16, so that's 10 to the power 4 per centimeter cube. That's the concentration of holes. Now it says, if the same piece of semiconductor already having Nd of this much is also doped with Na of 2 into 10 to the power 16 acceptor per centimeter cube, what are the new equilibrium electron and hole concentration at 300 K? If that is done, we have to see what is the net concentration, and that will be, since Na is equal to 10 to the power 16, 2 into 10 to the power 16, and Nd equals to just 10 to the power 16. So the net effect is of course acceptor type, so net is acceptor, which is 2 into 10 to the power 16 minus 10 to the power 16, which results in 10 to the power 16. So now the P will be equals to, we are assuming full ionization will be 10 to the power 16 per centimeter cube, and as before, but now N will be just the previous calculation, but now for N will be Ni square over P, and the same thing, same values, so Ni is 10 to the power, the intrinsic concentration is the same, so that's 10 to the power 10 square and 16, so that gives 10 to the power 4 per centimeter cube. Now this is the electron concentration, because when donor doping was present, acceptor doping was twice of that. Additional acceptor doping was done. As a result, it has become p-type. It asks what is the Fermi level position as with respect to the intrinsic Fermi level. So if we use this formula, since this is p-type, we should write EI minus EF equals to KT ln of, that will be P over Ni, so that is 8.6173 into 10 to the power minus 5, which is Boltzmann constant, times 300 times ln of 10 to the power 16 over 10 to the power 10, which equals to 0.36 electron volt. So that's the difference, that's the separation between intrinsic Fermi level and the Fermi level.